We've talked about molecular shapes, and we've also talked about the polarity of bonds. And so now we're going to put those two ideas together and learn how we can identify whether a molecule itself is polar or not. If we have a diatomic molecule where we just have two atoms, there is only one bond. Example here, hydrogen and chlorine. There's one bond. If that bond is polar, then the molecule is polar. And remember, a polar bond is one where the electrons are not shared equally. We talked about, the little boys playing in hydrogen's house, black and white television, not very fun to be over there. Fluorine's house is like super, super cool. And so the two boys playing together spend more time around Fluorine's house because it's more attractive to them, right? And electronegativity is that measure of how attractive is an atom for electrons in a covalent bond. So here, chlorine is more electronegative, and again, we can assess that using the periodic table. Fluorine is the most electronegative, and so if you look at two different nonmetals, whichever one is closest to fluorine on the table is going to be more electronegative than the other one. So here, chlorine is much closer to fluorine than hydrogen. This is more electronegative, so the electrons are going to spend more time over here. And this arrow is like, somebody coming to the house and dad's out mowing the lawn and they're like, where are the boys? And he points. They're over there. They're at the more attractive house because that's where they spend most of their time. So this is pointing to the negative end, and to help us remember that, there's a little positive symbol on the other end. If we look at the electron density, we see that the electron density is higher over here. The electrons are spending more time over here, and that's what makes this end of the molecule a little bit negative and this end a little bit positive. It's not like an ion where you've transferred the electrons. The electrons are still shared, but they're not shared equally. Any questions? When we get to more than two atoms, then we have to look at the polarity of the bonds and the shape of the molecule to see if the dipole moments are going to cancel out. And a dipole moment is just this imbalance in charge, where we have a negative end and a positive end. So let's look at carbon dioxide. Carbon dioxide has two polar bonds. It is a linear molecule because there's no lone pairs on the central atom, and there are two electron groups. So each of these bonds is polar. Oxygen is more electronegative, and so it's pulling the electrons away from carbon. This oxygen is pulling the electrons away from carbon. But because it is symmetrical, because both oxygens are pulling away from carbon, we don't end up with one end of the molecule that's negative and one end that's positive, right? So if we look at the electron density is a little bit less in the middle, but it's the same on both ends. And so this is a nonpolar molecule, even though it has polar bonds. So another way we can think about this is people playing tug-of-war. So that's one of those games that they don't do much in elementary school anymore because people could get hurt, right? Yeah. People get hurt walking down the street. So, you got the little flag in the middle here, and you got a person at each end, and they're pulling on the rope, right? And if one person is stronger than the other, the flag will move in their direction because they're pulling the whole contraption here, both people and the rope, they're pulling them over, right? So that would be like a polar molecule. If this oxygen was pulling on the electrons more than that one was, then this would be lopsided. But here, the people pulling are equal in strength. And so it's just going to look like nothing's happening because they're both pulling as hard as they can, but because they're both the same strength, nothing happens. Okay, the flag doesn't move. Does that make sense? These dipole moments are actually vectors. I don't know if you remember those from math. Probably blocked those out. Vectors have a direction and a magnitude. And so the dipole moment is a vector, and for the one bond it's going to the left, and for the other bond it's going to the right. The length of the arrow represents the magnitude, and then the direction is the direction. So here, these two vectors are exactly opposing each other, and they're equal to each other, and so they cancel each other out. So the magnitude of the dipole moment relates to the electronegativity difference between the bonding atoms. So this is carbon and oxygen, that's carbon and oxygen. The magnitudes are the same. And the direction is going to point towards the more electronegative element, which is the oxygen. So it's pointing this way, and the other one's pointing that way. They're opposing each other. So let's look at a little bit more. Let's look at water. Water also has polar bonds. If we look at the Lewis structure for water, we see that there are two lone pairs on the central atom, and there are two bonding pairs. So this is a total of 4 electron groups. And then we think, well, what do 4 balloons do when you tie them together? What shape do they make? Tetrahedron. Tetra means 4. So this makes a tetrahedron, but those lone pairs are like invisible balloons, and so the molecular shape is like this, and it's just called bent. When you just look at the Lewis structure, you might think that water's linear, but it's not. It's bent because of those lone pairs. So here we have 2 polar bonds, and again, the oxygen's more electronegative, so it's pulling electron density away from the hydrogen, and it's also pulling electron density away from this hydrogen. So the magnitudes of those dipole moments, those vectors, are equal, but now the direction is different. In the other example, they were exactly opposing each other, and here they're going at angles, right? So if we add these 2 vectors, we end up with this one in the middle, and the oxygen end of this molecule is going to be more negative, and the hydrogen end is going to be more positive. And again, we could think of this as, playing tug-of-war again. So here we've got, I didn't mean him to look like that, but that's okay. There's Dad. And here's one of his twin sons, and here's the other twin son. And so these 2 little guys are equal in strength. It just really doesn't look like a dad at all, does it? Sorry about that. Not an artist. But Dad's a lot stronger. So can you imagine what would happen? Dad's got an arm out, and he's pulling on a rope with each boy, but he's stronger. He's going to be able to just back up and pull those kids along, right? So in the tug-of-war way, then this is moving, right? And so there will be movement here, and so it'll be a polar molecule. Any questions? So this is the way the book tells us to determine polarity. We have to start with the Lewis structure and determine the molecular geometry. We need the Lewis structure because we need to know how many electron groups and if there are any lone pairs. Then you need to identify if the molecule has any polar bonds. If all the bonds in the molecule are nonpolar, then it can't be a polar molecule, right? So the nonpolar bonds would be if you have 2 elements that are the same, like 2 iodines, that's going to be a nonpolar bond, or carbon and hydrogen. If you have any other 2 nonmetals, in Chem 1A, you should predict that that's a polar bond. That's not always true, but it's true enough for Chem 1A, and it works pretty well in OChem 2. So then, the rigorous way is you would indicate where the polar bonds are, and you draw the vectors. The length is going to be proportional to the difference in electronegativity, and then you have to determine if those vectors add up to a net dipole moment or if they cancel out to zero. That doesn't sound very fun, does it? Let's do this one. A molecule contains 3 identical polar bonds in a trigonal planar molecular geometry. Is the molecule polar? Well, let's just kind of think about this. We've got 3 identical polar bonds, right? And it's trigonal planar. So it's a perfect triangle. So we've got one here and one here, and they're the same length. I'm trying to make them the same length. It's not working out so well. So this is like one person or maybe an object, and 3 people are pulling on it, but they're equally spaced out and they're equally strong. Is anybody going to be winning here? No. It's going to be static. They're like pulling and pulling, but nobody's getting anywhere. So this is a nonpolar molecule. These vectors, because they're the same size and they're symmetrically spaced against each other, are going to add to 0. So is this molecule polar? No. No, it's not. I'm going to go through this very quickly because you can be very successful in this class without understanding vector addition. But vector addition in one dimension is very understandable. It's really just adding numbers, right? So here we have 2 vectors. They are equal in magnitude. They're both 5, and they're in the same direction. So this is like a number line, right? We start here and we move over 5, and then we move over another 5. 5 plus 5 is 10. And so the sum of those is this, longer vector. Does that make sense? Here we have a vector with a magnitude of 5 that's going to the left, and a vector with a magnitude of 10 that's going to the right. So this is like plus 10 being added to minus 5. And the sum of that is also going to be non-zero. It's going to be positive 5. You could also think of that as being like, okay, so I'm starting here, and I'm going to go negative 5, 1, 2, 3, 4, 5, and then I'm going to go positive 10. So wait a minute. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so the net result there is this part, right? So they don't add up to 0. Here we've got positive 5 and negative 5. They're the same size and they're exactly opposite directions. So you add those together and you get 0. That's what we're talking about with vector addition. Any questions about that? In 2 dimensions, what you would do is you would take your 2 vectors and have the positive ends together, and then you're going to draw a parallelogram, and the sum of those is going to be the diagonal of the parallelogram. And then if you have 3 or more, you're going to add 2 of them together, and then you're going to add the 3rd one to the sum of the first 2. This is just kind of showing us some of the common situations. We can have a linear molecule with, and all of these are looking at equal magnitudes of dipole moments. In a linear molecule, those things are going to oppose each other, whether it's pulling against each other or pushing towards each other, and that will be nonpolar. It's symmetrical. Trigonal planar, again, we have things separated equally in space, they're equal in size. This is going to be nonpolar. Tetrahedral, also going to be nonpolar if the magnitudes are the same because they're all pulling against each other. In a bent molecule, though, this will end up being polar because these dipole moments are oriented differently, and so they're not adding up to 0. Also, with a trigonal pyramid, we're going to end up with a polar molecule. What causes a molecule to have a bent structure? What does it have to have on the central atom? It has to have lone pairs, right? A linear molecule most of the time does not have lone pairs. Trigonal planar doesn't have lone pairs. The only exceptions there are if you had one of those expanded octets, like a trigonal bipyramid, and you had 3 lone pairs, you could end up with a linear molecule. But we're not going to ask you to do ones like that. What's also on the central atom if you end up with trigonal pyramid? Does it have a lone pair? Yeah, it has a lone pair. Because this comes from tetrahedral electron geometry and one of these being a lone pair. So when we have lone pairs on the central atom, we almost always have polar molecules. So this leads to my simpler method of identifying whether a molecule is polar or not. And being able to identify the polarity of a molecule is pretty important. So here are the rules. There's only 2. A molecule is nonpolar if both of these things are true. No lone pairs on the central atom, and all the atoms bonded to the central atom are the same, or they have the same electronegativity. Because without any lone pairs, the vectors are going to be spaced equally in space, and they're going to oppose each other. If the magnitudes of those vectors are all the same, then they're going to add up to 0, and the molecule will be nonpolar. So let's do an example or 2 here. Determine if CF4 is polar. Well, we still need to start with the Lewis structure. So we're going to draw the Lewis structure. We've got 4 fluorines, and then if we go and add up all the electrons, we're going to end up with something that looks like this. What we're interested in is the central atom. Are there any lone pairs on the central atom? No. So that's condition 1, no lone pairs on the central atom. Are all of the atoms bonded to it the same?
Yes.
Yes. So both conditions are met, and that means that this is nonpolar. And we can identify that just by looking at the Lewis structure. We don't have to look at the shape and add up vectors. Any questions about that? So let's do, whoops.
What did you say about the electronegativity again? You said if the electronegativity is the same as...
If the electronegativity of all of these is the same.
Okay.
So there are situations where, you can have different nonmetals that actually have the same electronegativity. Like carbon and sulfur is one that I happen to remember. So if these were different but they had the same electronegativity, it could also be nonpolar.
Okay.
But I'm not going to ask you about any of those.
Okay.
So let's look at another example. And here, instead of fluorine, let's say we have something else. Maybe bromine in there instead. And we want to identify, is this polar? Well, are there any lone pairs on the central atom? No. Are all of these atoms the same that are bonded to it? No. The bromine is different, right? So these 3 dipole moments, these 3 vectors are all going to have the same magnitude, but this one is going to have a different magnitude, right? And so now it's not going to add up to 0 anymore. We don't need to think about what is it going to add up to, but just that it's non-zero. So this is going to be a polar molecule. One end is going to be more positive and one's more negative. Any questions? So, yeah, question?
I was going to say, so you said, so it's on the central atom, so what if you have 2 central atoms? How did you...
If you have two central atoms, then it gets a little more complicated. There, you can pretty much look at it and say, well, is this molecule really symmetrical or not? Molecules that are symmetrical tend to be nonpolar. Molecules that are polar often have lone pairs on one or more of the central atoms.
Okay.
Yeah. And the one kind of bond that you should remember is nonpolar is carbon-hydrogen. So just, going along with that, let's make up an example, and let's say like ethanol
Those ones are pretty
or
small.
methanol. Just do methanol, it's a little smaller.
What about the oxygen?
So there's two central atoms there, right? There's this one, and there's that one. If we look at this one and say, well, does it have lone pairs? No, it doesn't. But are all the atoms bonded to it the same or have the same electronegativity?
No.
No. So that suggests polar. And here, if we look at this oxygen, are there lone pairs in the central atom? Yeah. So polar. This is a polar molecule.
So like with the anes though, like those would be nonpolar.
Correct. If you just have all carbons and hydrogens, it doesn't matter what shape they are. They're going to be nonpolar because all the bonds are nonpolar. Yeah, good questions. Yeah, alkanes. Okay, so this is important because polar and nonpolar molecules have different properties. So I think we all recognize that oil and water don't mix, right? Italian salad dressing, it's got oil and vinegar and water in there, and you can mix it up. But if you sit there and watch it for a minute, it starts to separate again. And that's because oil is nonpolar and water and vinegar are polar. So here we're looking at models of water molecules, which we previously determined are polar. The oxygen end is negative, and the hydrogen ends are slightly positive. So the hydrogen end of one water molecule is attracted to the negative end of a neighboring water molecule. And we'll learn later on that those are called hydrogen bonds. But that's a force of attraction between the molecules. So water molecules are attracted to each other, much like little magnets, north and south pole. They attract each other, right? And so they're going to stick together pretty well. Oil is nonpolar. It's just carbons and hydrogens. So it's nonpolar. It doesn't have these kind of magnetic attractions. So it's a little bit like if you took a bunch of magnetic marbles and a bunch of regular glass marbles. Right? The magnetic marbles are going to all clump together, and they're going to squeeze out the glass marbles, right? Because these don't share that same kind of attraction that these have. So when we mix water and oil, we can shake it up and get little globs of the oil to disperse through the water, but as soon as we stop shaking it, the water is just like finding each other and squeezing together and pushing the oil out. The oil's going to float on the water because it's less dense. There are other nonpolar substances that will sink in water, but they'll also form a layer. Any questions about that? So now we can explain how soap works. So I think we all know from experience that if you get butter or grease or something on your hands, you can't just use water and rinse it off. Doesn't matter, it's just not going to come off, right? Because grease and oil don't mix with water because grease and oil are nonpolar and water is polar. So soap molecules help the grease to get into the water so it can be washed away. So soap molecules look something like this. They have this long hydrocarbon tail, which is nonpolar, and that mixes in really well with the grease that is nonpolar. But one end of this is polar. And so the polar end will interact with water really well. And so what happens here is you've got some grease, and you're going to have the nonpolar tails of the soap are going to get into the grease, and then the polar heads are going to be on the outside of the grease because the grease and the polar heads don't get along with each other. But now you have this little micelle that has negative charges on the outside, and that is attracted to the water molecules. It's like speaking the same language. And so the water molecules recognize these polar heads and are like, hey, come on in, right? We're attracted to you, get on in here. And so in this way, soap can take grease and break it up into little tiny chunks, surrounding it with the heads of the soap molecules, and then it can sneak away in the water. And that's how soap works. Any questions?